Welcome everybody to the panel session on day 2 of the Collegeville Workshop, 2020 Collegeville Workshop on Scientific Software. We failed to turn on recording to the beginning of this panel, and so I'm just recording a little bit of the content from that beginning. We're going to paste that on to the real recording. And so I apologize to the panelists and the audience for not having that captured from the raw content. But let's get started anyway. So, first, we thank our sponsors for who helped with us hosting this event. Intel Corporation and the MathWorks Incorporated both provided funds that allowed us to have students work and support the conference. And the College of St. Benedict and St. John's University are the host institution, home institutions, and also the host of the Zoom resources that we've used for this meeting. So thank you very much. We talked a bit about the meeting purpose that in the earlier panels. We're attempting in this event to bring academia and industry and the labs, staff from these types of institutions together to explore our common needs and differences and complementarities, and to build knowledge and awareness to improve productivity. And really the purpose of the Collegeville Workshop and its series is to build community in this area. This was a meeting workshop agenda. We did a lot of recordings of videos and collected white papers on content. All of this information is available on the Collegeville 2020 Workshop website. We used Slack during the meeting, and I think quite effectively. And now let's move on to the introduction of the panel 2, which was focused on technical approaches to improve productivity. We had 6 panelists, and Pat Quillen from the MathWorks was the moderator. Vivek Sarkar is the one panelist whose content we didn't capture, opening remarks. These are his slides right here, his particular slide right here. And so I'll let you take a look at that as I talk a little bit about what Vivek has spoke. So one big theme of Vivek's work recently has been asynchronous tasking as an approach to improve productivity, and also Python-based runtimes for improve productivity of the people who are developing and using software. In fact, Vivek and the team that he works with have a recorded video on this topic, as well as a white paper on it. And so I encourage you to go and take a look at it. Our second panelist was Jason Gates, and we managed to capture some of his introduction. But here you can see the slide, and then from here we'll pause and move over to the live show. Thank you.
I guess the way I think of it is, if my head is so full of physics I can't appropriately devote time to developing a DevOps infrastructure, I need someone who can focus on that infrastructure so I can spend my time on the physics. And those are kind of the 2 key things I see in making this sort of approach work. In terms of potential impact, what we've seen and what we shot for is just substantial improvements in replicability, significantly decreased debugging time and frustration. It's kind of like as close as you could possibly get to an easy button. In this particular context, you want that as much as possible. And then also, even though there's kind of significant investment effort up front to get things in place and up and running, all of that investment pays dividends after the fact, because you wind up accelerating the development of this infrastructure, such that when your team asks you, can we insert, whatever the feature is here to our continuous integration system or something like that, it's relatively straightforward to do so and relatively easy to maintain after the fact. The main bright spot I see in terms of signs of progress is with the handful of teams I've worked with. Some have been really willing to take the plunge, to bite the bullet, and do all the investment in this kind of infrastructure, and they're seeing the dividends. They've seen the payoff, and they're able to tell other teams, like, hey, this is all that we've experienced in the last few years, and it's awesome, and you should do the same. Whereas other teams who are initially hesitant, like, I think we're just going to keep, plugging away, hacking bit by bit, and kind of try to make incremental improvements. And we know we should do like the major overhaul to our build system, but we'll think about that some other time. You have the ability for these teams to talk to one another and really share success stories. And it's one thing for the DevOps engineer to say, you should do this, it's going to be good for you. It's kind of like eating your Wheaties for breakfast. I know I should do it, but I don't want to. I want the Cinnamon Toast Crunch. But if another team comes to you and says, hey, this is what we did, and we were skeptical at first, but oh man, there's no way I would go back to the way things were before. That's a much more powerful story to communicate. So that's what I got.
Yeah, excellent. Thank you. Yeah, it's funny to me how the ilities always keep showing up, and what an impact on both productivity and quality. Thinking about those things and trying to push them forward is. So that's great. Thanks, Jason. I appreciate it. All right, Charles, you're up.
Okay, can everyone hear me?
I can, yeah. I think so.
Okay, sounds good. All right, as Pat said earlier, I'm Charles Ferenbaugh from Los Alamos National Laboratory, and I should give you a little bit of my background so you can understand where I'm coming from. I've spent a lot of my time at Los Alamos working on projects that have been running for decades, writing large multi-physics codes, and are often kind of set in their ways. And I'm working on a project that has been like that and is transitioning to more modern practices. So hear what I'm saying in the context of that project. One of the things we've seen that really has been a productivity improvement for us is implementing a robust testing system, which to some of you that may not seem like much, but for our project, it was a huge thing. And when we started this refactoring effort about 5 or so years ago now, there was a set of integrated tests that was only partly maintained. It was not necessarily reliable as a testing framework. So as part of the refactoring effort, we had the project made a commitment to take that integrated test suite, get everything running, and keep it running reliably on a regular basis so that developers could rely on, if I go to run the test suite, I can expect everything to pass unless I mess something up. So that was one of the first things. Alongside that, we also put in a unit testing system to complement the integrated tests. And the key roles in making that happen were we needed some developers to go in and set up a testing framework to deploy it within this large existing code, and to deploy it in a way that made it easy for other developers to use, so that there wasn't a huge learning curve for saying, okay, go write a unit test or go implement an integrated test for this capability you're adding or this capability you're modifying. So that's one of the key roles. The other key role, which is perhaps to some people it might be an invisible one, but it's a very important one, is to have management support for the upfront time investment it takes to get your testing system up and running and usable. And in the context of the context of the project I was working on, we had, for a long time, there had been a culture of just put physics features in as fast as you can. Anything that's not on the critical path to getting your physics feature in is a waste of time. So it took a kind of cultural shift to support that. Unfortunately, we had management that was ready to make that cultural shift so that the upfront time that it took to get the testing system going was, it was understood that yes, there'd be a little cost up front, but it would have a big payoff down the road. And management was willing to take that on, and that was crucial to making all of this work. And so as you all probably know, having a good testing system, the potential impact is that having testing very early on to verify your correctness can greatly reduce your errors either in your initial development of code or in any modifications, refactoring, debugging that you have to do, any modification that you have to do later. It can reduce your errors and reduce the amount of time you need to spend debugging by catching those up front in your testing system. So a couple of the bright spots that we've seen from doing that are that we have had this cultural shift that writing your tests and running them when you make changes has become a regular part of developer workflow. It's just a completely accepted part of what people do, both in their initial development of code and when they're doing changes to the code, refactoring, modifications, whatever. That's completely a normal part of the workflow. The other thing, which was one I didn't expect, but has turned out to be a nice bonus, is that people have come up with creative ways to use the test system for things that we didn't initially intend it for, but are useful for improving productivity. We have an effort going on to take some of our existing Fortran kernels and rewrite them in C++, and then rewrite them using Cocos for running on novel architectures like GPUs. And one of the developers came up with the idea of using the unit test framework to run the original kernel and the new kernel side by side and verify that they've had the same result, and doing that on a regular basis as they do this this novel architecture version. And that's been a big plus for their development. We've also had an effort going on where we're integrating a third-party library in the code, and we've used the unit test framework to verify that our wrappers to integrate that library are working properly and doing what we expect, even before we plug it into any of the physics. And that, again, that has been a big win for us in terms of finding potential errors up front before we have to separate them from the new physics code that uses them. So that's been a big win for us. And that's what I have.
Great, thank you very much, Charles. Yeah, testing systems, they definitely can help productivity. Excellent. Yes, great. Moving on, now we have Vadim Dyadechko from ExxonMobil with his opening thoughts.
Hello, everyone. So I decided not to talk about specific technical tasks or technical improvements, and rather address the general principles and the mindset which leads to improvement in the software product pipeline. One of the reasons is that we all have a little bit different environment. We all have a little bit different hardware system. We'll have a little bit different products. And talking about specific details may not project directly on what you do. So I like this quote from Anna Karenina by Leo Tolstoy. Right at the beginning of the novel, he says that all happy families I like, and each unhappy family is unhappy in its own way. So nobody but ourselves can help to solve our problems. But at the same time, it's important to understand where we should go and keep in mind that there's a big picture. So first of all, This is not an approach. This is more like a mindset. You really have to stop looking for silver bullet. There's no silver bullet. You really have to roll up your sleeves and start improving your system one little step at a time. The most important thing is really reduce all non-essential complexity in your product, in your environment, in your processes. You will be surprised, once you start doing it, you will be surprised and start qualifying your features and your processes into two categories, essential and nice to have. You'll be surprised how many of those fall into category of nice to have. And it requires a lot of will and a lot of determinism in order to reduce that complexity. And the last one, you really have to streamline your routine tasks. I deliberately didn't say automate, because there's a lot of things beyond automation that can help your process. Like, for example, having onboarding instructions for your new team members readily available, and not just readily available, but evergreen, always tested, so that the person who start implementing them step by step will not run into surprise. So all your routine tasks should take zero effort and be really human-proof. This human-proof property guarantees that you will not waste your time on resolving unnecessary conflicts and chasing unnecessary errors, I would say. The key success in implementation is really to have everybody on board. I will echo the previous speakers and just note that it's important to raise awareness of your goals, motives, and challenges in order to secure support. Secure support among your colleagues, among the team members. Most importantly, you have to have support of your management. These things require a lot of time investment, and the results may be seen only in the long run. So everybody should understand why you do it, and by do it, I mean focusing on continuous integration, focusing on DevOps, focusing on reducing the complexity, and what's the benefit for everybody. The processes in your organization or in your system, in your community, should be really aligned so that they motivate positive change. If performance of software developer is evaluated based on the number of publications, not on the impact that his improvement have on a team, you will be struggling in order to improve your automation, in order to improve the processes in your team. So the potential impact of streamlining and automating on routine tasks is really more transparent, robust, and low overhead operations. You will stop wasting your time, like I said, and concentrate on things that really matter. For growing your product, you will spend the time on growing your product rather than fighting these little hiccups. And there's several bright spots I would like to mention. So Git and Spec, these are the products that represent very good examples of streamlining routine tasks. So Git, I would even say Git revolution that happened last probably decade, changed completely the way we address the version control. There's a nice presentation by Jason and Ross, Git productivity. I encourage everybody to watch that video. And if your team is not on Git right now, now is the time. I would say yesterday was the time, but it's never late. There's a great product by Todd called Spec. And I'm glad that Department of Energy found time and resources in order to support this product. I think it was one of the key products in the exascale software stack. So once again, there's a nice presentation by Todd. Go watch it. I see things happening around, And one of the positive sign is really growing awareness of operational complexity. I do see people refusing to implement certain features or even share code based on the fact that it creates unnecessary dependence for them. I had, the last year I had conversation with several colleagues from DOE, and they all mentioned that they work on feature A. And when I had the third conversation about this feature A, I asked, why don't you guys use whatever the previous team developed? And the straightforward answer was, we don't want this dependency. We have a little bit different product. We have a little bit different setup. We don't want to share our code. We're not asking for help from anybody else. This is just an easier way of running stuff and getting in everything streamlined and not having dependencies on any third party. That's it.
Great, thank you, Vadim. Thank you. A lot of things starting to arise here between DevOps, CI, testing, and the investment or the buy-in from management being necessary. So some real themes arising here. All right, Anshu, it's your turn. Take it away.
Thank you, Pat. So a little bit of my background too, like Charles, I've been swimming in these waters for a very long time, starting about 2003 and flailing quite a bit, because when I started in this business, there was even less of an ecosystem for large-scale scientific software to be developed and have any kind of software engineering support. So in many ways, in those days, we ended up building our own tools, our own methodologies, our own practices. And because they were driven by our own requirements, what I have found to be true is that till today, they continue to be far more useful to us than what has become available over the years. That's not to say that it's not a good thing that there's lots more available, but certain of the things, for instance, the one that I've decided to focus on here is an example of things that we found to be extremely useful, and yet they still don't bubble up to anywhere near the top to become a topic of discussion among people, practitioners in the field. So one of those things is this a custom testing harness. So you can think about it, we are working in a mode where there is no Git. So we are working with SVN, which means that there is no concept of a pull request. People check into the trunk as and when they develop code. And we are working with a multi-component, multi-physics code, which means that even if people are being diligent and testing their code before they check in, they don't have a reasonable mechanism of exercising the interoperability that exists necessarily in the code. And so people check in their code and the test suite runs and there's a bloodbath because a lot of tests failed. The test that the developer was working with passed, but a lot of tests failed because there was no easy, simple way for him or her to test the interoperability impact that their development was having. So as we built our own testing harness, because in those days there didn't used to be Jenkins. And so one of the features that we built into that testing harness was this ability for the developers to down select the tests from the entire test suite that they could then run at will, didn't have to wait for the cron job to launch it every night, but they could run it at will. And the results would still show up on the same web page where the results of the regular testing showed up. And this was an incredible help in making sure that the inadvertent violations of interoperability correctness did not make their way into the code. And so the role that would be that the person that would be taking on this role would usually be a testing verification lead of the project. And this, in many ways, was a very good tool for helping us keep our code and our test suite passing much more frequently than it would have otherwise. And we have used this method quite extensively in the past. It's very easy to implement. In fact, for a brief period of time, I was working with the E3SM project, and I convinced them to start using the same harness in the same way that we were using. So it is something that is available for people to use. But other than that, of course, I echo things that have gone before, that people have said before me, in that you have to have a comprehensive set of practices that in some sense you have to evaluate with regard to adoption in your team, and adopt them in ways that basically maximizes the productivity of your team. So you let the research inform your practices and your adoptions rather than telling you, in the sense that you don't have to adopt what the research tells you is a thing that works for everyone. You can still customize it for yourself. And that's the approach we've taken always. That's all.
Excellent, great. Thank you so much, Anshu. You know, testing harnesses are so critical, I think, to productivity as well as to quality. And, you know, part of that I hear, I keep hearing the cultural approaches leak in. It's incredible to me how the cultural and the technical always seem to blend together. You know, where you have to both inform people on how to use things, get your team dedicated to it, have management buy-in, and the whole 9 yards. I think this is good stuff. Thank you. And finally, Hartwig.
Yeah, thanks, Pat, for running that panel, and also thank you, Mike, for inviting me. So maybe also some background about myself. I'm coming from math and do software development, specifically math software development, for more than 10 years now. I initially wrote Magma Sparse, which is the GPU focused, or let's say NVIDIA GPU focused code. And just 3 years ago, I started my own group, and we started a software package called Ginkgo, where I kind of had the chance to undo all the mistakes that I did in Magma Sparse and do it more sustainable. And in this context, I also want to mention XSDK, where we are involved in, that is led by Ulrike Meyer-Yang, and provides a lot of useful input, and also the Better Scientific Software community or web page that is run by Lewis and Mike, and also brings a lot of useful tools. So one or two high impact technical approaches, I actually have three. So one is clear software development cycles and support those by scripts. These scripts can, for example, generate boilerplate code or files, or tests, unit tests, or convert files, for example, from CUDA to HIP. So these scripts are an extreme help if you are onboarding new members. So if they have never written code in a certain library, they don't know how to structure that. So if you have scripts and you tell them, hey, there's a script, just create algorithm, and then you will see in your Git or log that you have new files, and then you can go to the files, and then there's this description. Okay, here's where your algorithm should go live. Here's where your headers should go. Here's where you put your kernels. That is extremely helpful if onboarding new members, and it also removes a lot burden in terms of writing boilerplate code, where we all know how the code will look like. We just have to write it, and gives the developers the possibility to more focus on optimizing kernels for specific architectures. Another, of course, is continuous integration, and that includes exhaustive unit testing using Google Test. Google Test is an excellent tool. So we currently have 95% coverage, and there is no pull request going into Ginkgo without unit tests. So that is like a rule. Nobody can contribute anything if he hasn't written unit tests for that. And writing unit tests is not easy. It's sometimes harder to write the unit tests than the algorithm itself. And then as we have a very comprehensive continuous integration framework that tests for roughly 20 or 30 architectures and compilers and operating systems, it's at a level where all the combinations are hard to manage. And we have an automated Docker image generation such that we do not have to generate all these Docker images and update them with the new compilers and libraries by hand. But there is like an automation, an automated process that actually generates these Docker images. And again, this of course helps in terms of the people, the developers can more focus on the actual software implementation. Key roles. Of course, there are people that set up all these frameworks, and it's important that they also document that setup. Because maybe they will move on to another place, and then nobody knows how it was that working, how was that automated Docker image generation working, and so on. So document all these frameworks. And then for me as a project lead, this was actually a very important step, because I could basically say, hey, I'm writing math libraries for like 10 years, and now you come here with your master degree and you want to tell me how to do stuff. No, it's the other way around. I'm kind of stuck in my old-fashioned views, and it's very important that I actually listen to the people, because they are doing that every day. I'm mostly working on administrative stuff, unfortunately, but they do that all the time, and they know what is going wrong, and they know what is working. So it's very, very important for me as a project lead that I listen to what my people tell me. And in most of the cases, they are actually right, and I'm wrong. So maybe a bright spot that I can tell in terms of how these frameworks work out. So we extended Ginkgo scope from NVIDIA GPUs to also cover AMD GPUs. And basically this was done by mostly one PhD student within 4 weeks. Afterwards, we needed some performance tuning, but other than that, this is like a great achievement. And I think this is due because of the very comprehensive continuous integration framework, and also because we have these scripts that make it very easy to extend the library. Thank you.
Great, thank you very much, Hartwig. All great things. That's pretty impressive that you're able to move from NVIDIA to AMD GPUs in just 4 weeks. I think that's actually pretty incredible. Before we start opening things up to the rest of the panel, I do have a question about that specifically. Do you think the key behind that was your collection of scripts to support that?
That was an important aspect. Another important aspect was that we decided in Ginkgo that, okay, we are facing a very heterogeneous world. And instead of making the mistake that I did with Magma Sparse, where I basically focused on one architecture specifically, we said, okay, let's completely decouple the algorithms from the backend. So we basically have the algorithms, the library core, and these algorithms cannot work without a backend. And then we basically interface the respective backend on the respective hardware architecture. And all that works through runtime polymorphism, so the user wouldn't see that. And it makes it very easy to add backends and to remove backends.
So you've architected for essentially productivity.
Yeah, we've architected, we've designed the library for cross-platform portability, because we think that platform portability is maybe the most important aspect in what makes software sustainable.
Great, excellent. So thank you all. Thank you all panelists for your opening remarks. We're going to begin opening it up for questions and discussion. Again, the Q&A protocol is simple. I see the Zoom chat's already starting to fill up with a little bit. When your question is mentioned, we'll go ahead and unmute you, or please unmute yourself and ask it verbally. And of course, unless you're asked to speak, it's always good to stay muted. And again, with the general chat, please, fill up day 2 chat. I've seen a lot of activity out there, a lot of talk about heterogeneity. So your last comments there, Hartwig, will kind of blend right into, I think, the first questions we have. We'll stop at 11:30 Central, or when there's no more questions. And I'm going to go ahead and stop screen sharing now so we can see everybody's smiling face. So, all right. So I think the first thing, and Alex, forgive me for stepping on your job here, but the first thing I see in the chat here is a comment from Teresa. You'd definitely like to hear more about tools for heterogeneity. Teresa, do you have something to add there for the panel?
Yeah, I mean, we heard it from several people about, there are better tools to do this, especially with asynchronous communication, there's highly scalable computing. And we also heard from Hartwig just now about this mapping between CUDA and HIP. The comment I'd make is that CUDA and HIP is kind of a much more straightforward direct mapping. There's also the Intel GPUs that we now need to worry about, where the mapping is not necessarily going to be quite so straightforward. So anything along those lines of tools for managing that would be most welcome.
So I'm happy to give an answer here. So for us, of course, it's relevant that we also move to Intel GPUs. We are talking to Intel people. So ECP and also Mike leading the software stack is an excellent opportunity to contact industry. And Intel, of course, has a high interest that people move from NVIDIA GPUs or AMD GPUs to Intel GPUs. So they are doing a very strong effort in, again, providing scripts that basically convert your code. We're working with them. We're looking into the scripts. My feeling is it will work. It will be, again, the first step will be a very small effort, I guess, again, maybe a few weeks. But after that, we don't know how Intel GPUs will work in terms of performance. I think, or I expect, it will be a harder optimization step than it was for the AMD GPUs. The AMD GPUs are, I'm sure that NVIDIA and AMD people will correct me, but I think in general, the design is rather similar. We don't know that about the Intel GPUs. But, and I also want to mention that there are other options. So while we write native backends for each architecture, there are portability layers, for example, Cocos, and they do a really good job. And basically, you write your kernels in Cocos, and then you can run on different architectures, and you also get a really good, good performance on different architectures. And then it's basically their job, and I'm sure they will do it very well. It's their job to port to Intel GPUs.
May I chime in here? So my take on the business of performance portability has always been that you have to examine the structure of your code and your data structures and organize them in a way where the semantics are controlled by your architecture as opposed to the programming model that you're working with. Then if you have done that, then plugging in a different programming model is a relatively simple thing to do. And this applies even if you're using tools like Cocos and Raja, because you get more out of them if you understand the structure of your code and you map it. So you decide how you want to map it rather than let the tool do the mapping for you. You always get more out of it. The other comment I want to make is that at least those of you who are involved with the ECP project, there is a series of panels being run on performance portability. The next one is on Thursday at 2 p.m. Central Time. So if you're interested in this topic, I would encourage you to attend those panels.
Just, Pat, if I can just add to that at the
Please.
higher level, I made a reference to, our thinking about algorithms that to change. That's not directly my area. I work more on programming systems, but I interact a lot with people who design applied math algorithms. I was talking to colleagues at Georgia Tech, including Rick Woodok and Srinivas Saluru. And increasingly, actually, when you write on the whiteboard, somehow a task-based algorithm seems quite easy to express. You get the idea and you show the task dependencies. And then there's the business of converting it into a programming notation and Cocos or any other framework. There's still a lack of formal algorithmic notation to be able to say, and we start seeing this in papers, like create a task to do this and wait for that task in line 3 and it may seem like a small thing, but I actually think that the practice of designing and expressing algorithms in a task way, that also needs to evolve, and that'll make it easier to then convert the codes. And so there's definitely a gap there. In fact, there's a lack of notation at that pseudocode algorithmic level as well, because people immediately want to dive to some programming notation of a specific programming system. So I think for people who work at the algorithmic level, there's a great opportunity there.
Yeah, no, I agree with you, because we get performance despite the programming models, not because of them.
Oh, yeah.
Oh, I don't know that I'd go that far, but reorganizing your code will get you better performance independently of the programming model that you've chosen. We've seen that time and again.
Let me talk about a different aspect of heterogeneity, not heterogeneity inside of your code, but heterogeneity inside of your DevOps layer. So one of the motivations for having customized DevOps layer is to shield the heterogeneity and specifics of system available in the house from the end user. There was a comment in the day 2 chat about people have heterogeneous system, but at the same time they don't explore or utilize all the resources in optimal way. And most of my customers, they are not software engineers. They do their job. They're very busy, and their job is too hard even without HPC aspect. So one of the objectives of DevOps layer is really provide uniform environment for everybody and make all the tasks on HPC system straightforward and familiar. That's it.
All right, very good. Moving through the chat here, I see a question from Chris Seifert. He's got a question for Charles. Chris?
Sure. So Charles talked about a lot about the importance of testing, but as you write more code, you generate more tests, and so at some point the developer costs of maintaining the test suite will also be increasing with the number of tests. What are best practices here for managing the sort of ever increasing cost of maintaining your test suite?
I would say the number one best practice is having some form of running the tests regularly and fixing errors as soon as they're found. Ideally, somebody is going to catch an error, as they're making their change. They run their test suite and find, oh no, I broke this test, go fix it. I go fix it before I do my commit. Or there's we have for a long time had an automated script to run the tests nightly, and people look in the morning, if something's broken, it's high priority, get that fixed before the next nightly run. And the more modern form of that we're transitioning into is, of course, a CI system that runs these things on a regular basis as you're making the changes. But the point of all those is to say that if something breaks in the test suite, find it right away and fix it, instead of letting it accumulate and then having to say, oh my God, somebody's gonna have to go in and spend a week just fixing tests. You don't do that. You do it as it goes. I think the other thing I would add alongside is that there needs to be a willingness to keep an eye on the test suite and make sure that your test suite, you don't write fewer tests than you need, but you also don't write more tests than you need. I mean, do you really need 20 tests to test this particular part of the code, or is 3 going to be sufficient? So make sure that you get the most for your money in the tests that you write. Those are the two things I'd say. Does anybody else have anything to add to that?
I have a couple of words. Go ahead.
No, you go ahead because I'll take long.
All right. So I would like to add just a couple of things. So everything Charles said is correct. There is an issue, that's a downside of having very convenient regression or unit testing suite. People, if it's easy for people to add tests, they will start throwing them in indiscriminately. And maintaining your test suite is really a full-time job, or it becomes full-time job. So we have several rules in-house for maintaining. First of all, the timeout on all the regression test tasks is 1 minute, or if your scheduling system permits, you make it a fraction of a minute. Essentially, it does not allow people to check in tests that run too long. Second rule is all the tests should complete within 5 minutes. If we observe that the entire test suite takes more than 5 minutes to complete, then we sit down and make a review of all the tests, and either downside some of them or merge them. Like Charles said, there's no point of having a separate test for each feature. At least in the regression test department, you can combine multiple features in one test, and it is sufficient to have the safeguards against human errors. Over.
Okay,
Just
so
add something to that.
Shim, sure.
Yeah, another thing to keep in mind is that it's a good practice to have layers of test suites. We have one small test suite that's run on the CI every time somebody does a commit. We have a larger one that's run every night, and we have a still larger one that's run once a week. So you can get sort of the benefit of both worlds to have something that's run quickly on a very frequent basis. And if you have some tests that need to run longer, that's fine. You can do it on a less frequent basis and still run it regularly and have a wider range of possibilities of coverage that way.
Yeah,
Okay.
great.
So
go get them, Anshu.
I start with I start with shameless self-promotion. I actually wrote a paper on this. An entire paper about how you go about building a verification regime for a complex multi-component code. And part of it, and I've incorporated that into these better scientific software tutorials that we teach, the methodology for building a test suite where you provide adequate coverage without taking too long to run the test suite. And there is this very rigorous approach in terms of building a matrix where you tick off not only the capabilities, but also the interoperability issues that are important to your code in a matrix format, and you pick the easiest, the simplest test that will exercise that. And there is a whole sequence of steps and the sequence in which you pick the tests that form the basis of your test suite. So I'd be happy to provide the reference to anybody who's interested. And it is, like I said, also there. The tutorials are publicly available to see. So this entire methodology has been, at least the one that we use in our project, has been documented and is available.
That's great, Anshu. Thanks. If you would at some point paste in a link or some stuff to the day 2 chat, that'd be wonderful. I think people would appreciate it.
I will do that.
Excellent. Great discussion, everybody. Elaine has a question, actually, triggered by some of Vadim's comments. Elaine.
Oh, hi. Thank you, Pat. I really don't have much to add to this question, but I'm wondering if the panelists would mind responding just to this issue of hesitancy to have software dependency. Is it social? Is it socio-technical? Can you say a little bit more about this? Thank you.
If I may, I found this very great quote on the internet. I will post it later, which essentially says that third-party dependencies pose the greatest threat to any project, and at the same time, we cannot go without them. and you have to find your trade-off. The quality of components that you are using, they're varying. And people who develop those your dependencies, they have their own schedules and their own objectives, and they're not aligned with yours. One thing to remember. So you try to minimize the number of dependencies in order to minimize the time wasted on integrating those dependencies into your project. I find it very useful to execute the following strategy. If you just start in a pilot, you don't hesitate to use third-party dependencies. It's not a production code yet, and it allows you quickly to get fully functioning prototype. But as time permits, you start to get rid of these dependencies in implementing the functionality that they provide in your proprietary code. This way, you have opportunity to optimize this task specifically to your code, and at the same time, you potentially minimizing your maintenance and integration time in the future. Over.
Very good. Does anybody else on the panel have a comment about resistance to dependencies?
Well, I just want to throw in, and maybe we'll talk more about it later, using the growth of the Python ecosystem as an example of how to deal with third-party dependencies. And it's basically very evolutionary with survival of the fittest. So there are libraries that you can just check the volume of adoption that essentially, even if they're not standardized, they become de facto standards. So NumPy is a third part, started as a third-party library, but now no one uses Python for HPC without NumPy or SciPy. So just want to make a comment that, and maybe it's the obvious one, that keeping track of the adoption of the libraries that you're depending on ultimately gives you a good metric of your risk in using that library.
I only want to add that we've experienced, the hard experience of building a dependency and then not being able to go on a machine because that particular library has not yet been installed on that machine, or the funding agency decides not to continue to support it, are real hazards that you have to think about in adopting a library. And that people have been victimized by that a lot. And that's why people will not try to use bleeding edge software that comes around, at least for their production. They will wait to see it stabilize in the community before they adopt it.
Yeah, that's right. Any other thoughts about 3P dependencies?
So I think Vadim has or it was Vadim, right, who had that quote. It is an excellent quote.
It is.
Yeah. Dependencies, you also run into the danger that interfaces change. And in general, you don't want to see that. And I think maybe Trilinas is a good example that if there's an interface change, there's a long period where that is actually getting deprecated. So it's slowly fading out. Other libraries are more aggressive in deprecating functionality or interfaces. And that is a real danger for library or dependencies on other libraries. But at the same time, if we do not allow for any dependencies, of course, we don't the full potential. We don't use the full potential of what is out there. So it's a thin path. Yeah.
One more remark I'll make before we leave this question, and this is kind of more in a general sense, not just looking at TPL dependencies. I think it's fairly safe to say when someone makes a request of you to, bring in a new TPL, to add a new feature, to whatever, they're focusing on whatever the immediate problem is right in front of them, and they're not naturally going to see, the 2-year, 10-year consequences of making that change, whatever it is. So I would just encourage you all, in whatever kind of maintenance administrator type role you have with your projects, to be courageous in saying no. Like, it's okay to start with a no, or it's okay to start with a, I'm not convinced. Can you give me you know, some thorough reasoning on why this is absolutely needed and why it fits in well. Because from your perspective, I know you're trying to solve the problem that you're trying to solve, but from my perspective, I'm concerned about the maintenance cost moving forward. We just need to be okay kind of having those tough conversations, if that makes sense.
Absolutely. One of our directors here always says, if you're not saying no, you're not being strategic, which I think is always an interesting way to think about things.
I would
Great.
like to, oh, sorry. May?
By all means.
I would like to second the thought expressed by Jason about maintenance cost. Most developers, you know, I would like to use Boost as an example. It's very convenient because it looks like it's available almost everywhere. And nobody who never tried to install it and maintain knows how much pain it is to have a robust Boost on your system. And surprisingly, people who use Boost, they use just such a small fraction, like some sort of smart pointers or some buffers. Implementing this functionality in your code will take you no more than a week. And at the same time, you create a huge dependence on arguable quality piece of software, which is just, you know, conveniently maybe available and maybe not. I've seen change of attitude of people who move from developers to DevOps in their attitude towards using third-party dependencies. People who were advocating use existing third-party product, once they start performing DevOps duties, they suddenly realize how much pain it is and what it comes with. They feel the total price of this dependency. And this is why I think it is important to have some bridging between developers and the IT operations. This way people start to understand what it takes to do certain tasks and understand the true cost of everything. Over.
Yeah, absolutely.
That brings up the point that not all third-party libraries are created equal.
Yes.
Some of them put a great amount of effort into thinking, okay, not just how are we going to add all these new features, but how are we going to make it easy for people to use this, to install it, to move from one version to the next. Some third-party libraries put a great deal of thought into that and make it as easy as they can, and others don't pay attention to it quite so much. And that's one of the things you have to take into account when you're deciding whether to use a third-party library.
All good comments.
Some of the times you end up using a third-party library simply because it has an algorithm that is extremely difficult for you to implement for yourself, in which case you take all of the risks that come with it. Case in point, algebraic multigrid, which is a very difficult algorithm to use. So anybody who needs to use that will either use Trillinos or Hyper and not try to roll their own, as the saying goes. But so this is the other part of it, is that if a library is offering things that are easy to replicate by the team themselves, the chances are that they'd much rather do it themselves. But if it's a complicated enough thing and the value that the library brings is enough that doing it on your own is not worthwhile, or that you don't have the expertise to do it, then you will go with third-party library.
Yeah, very good. At the risk of introducing too much nonlinearity to the process, I'm noticing some third-party dependency comments lower in the chat, which, while we're on this subject, I think we could go ahead. Roscoe, you had a comment about third-party libraries, a couple of them.
Yeah, I mean, so the big problem with third-party library dependencies is their dependence on each other and forming these graphs of dependencies. If every dependency we had just had a single layer and they didn't interact with each other, third-party library dependencies would not be nearly as difficult or painful as they are right now. And my understanding is that with like Apple, with iOSS, is that the rule is that apps, for example, are not allowed to use other apps. So they solved this problem by forcing every app to go through the standard iOS API to get all features, so you can't depend on other apps. So, I mean, if we did that in HPC, it would certainly simplify our dependency management. The problem is that the HPC standard API is not nearly rich enough to support all the different things that we need. So that's a process that doesn't work. So it's, yeah, so yeah, I mean, deep stacks with third-party libraries is the biggest risk for any project, because all it takes is for one of those third-party libraries somewhere to do something really bad and break backward compatibility in a difficult way, and then it's a nightmare to try to upgrade any of your third-party libraries. It's called dependency hell, and there's been lots written about it. There's a standard that's been out there for quite a while called the semantic versioning standard, which is a very rigorous standard for how to go about how individual packages and third-party libraries can go about defining their versions consistent with their breaks and backward compatibility and deprecations and so forth. I mean, there's a lot of difficulty in implementing that, but if we implemented that on a broad scale inside of our community, then this would be much, much easier. Because the problem with SPAC is SPAC's great at just producing builds, but SPAC doesn't magically solve this problem of coming up with compatible sets of upgraded third-party libraries. There's nothing SPAC can really do with that. Someone has to figure out what those compatible versions are, create the patches to fix them, because you almost always need patches when you have a deep stack of third-party libraries if you want to upgrade them. So it's a real nightmare.
Great, thanks for the comment.
Yeah, your point about semantic versioning is one of the things I was getting at when you decide which third-party library to choose. If a project has committed to using semantic versioning, that means they will take on some of the discipline of controlling when and how they make changes and make your life easier. That's the mark of a good third-party library. That is a mark of a good third-party library.
Or they'll just upgrade their major version number every time they release.
Yeah.
And just be honest that they're
Okay.
breaking everything.
So some of these comments are dovetailing into a question from Mike also about third-party libraries and efforts at standardizing APIs. Mike?
Yeah, one of the things that I wonder about is, I put in MPI as an example, because you can write to the interface and then you have multiple backends that implement that. And could one of our efforts be to be much more aggressive in trying to standardize basic APIs for, key functionality? We've seen some nice examples of this in the recent history with XSDK. We've seen some nice kind of co-opetition between solver libraries. They see each other's results because they're both options in an application. Can we see more of that? And what are impediments to doing more of that?
Great question. Panelists?
The one possible impediment I see is the large amount of time that it takes, A, to decide on a standard API, and B, to make sure that it's implemented well enough by enough backends.
Mm.
It's a little bit of a chicken and egg problem.
What's that?
It's a little bit of a chicken and egg problem in the sense that how do you define an API when you don't know how the functionality is going to play out? But then if you don't have an API, how do you figure out how you're going to implement the functionality? So I think Vivek can speak to it because there was an attempt to standardize an API for tasking, right? And that proved to be a little premature.
Yeah, there's a lot of things, and one should not underestimate the non-technical aspects of this, or the political aspects as well. Which is why the reason I've been paying more attention as the Python ecosystem more recently is for a couple of reasons. Because people just vote with their feet; they don't wait for a standards body to tell them this is a standard API, and then it becomes very clear which is the dominant interface. So I think there's merit in it, and I think it's critical for productivity. to definitely have a common API, but we need to find ways to be more agile. Another thing that that's been on my mind much more in the recent years is the increasing number of people who are developing scientific software. You know, I mean, it was always true that scientific software included data analytics, but it's much more dominant nowadays. And people who develop that kind of scientific software don't have that ingrained HPC experience that you might presume from a classical HPC-oriented library. So I think another aspect there is how do you target the expertise level, you know, for a broader audience, and that's critical because actually ones who are not on their own, and so if you can, you know, get an API and an implementation that is more usable by non-experts, I think you may actually get more traction. But yeah, it is challenging, and you're right, Anshu, that it was ahead of its time in some ways, and there was definitely politics had its role to play as well.
Yeah, indeed.
I think common API is sort of like double razor sword. It helps a lot at the beginning of its existence and becomes impediment at the end. And vivid example is POSIX.io. A lot of nice things happened because it was introduced. And right now we all feel how restrictive it is. So I guess it's good to have API. One thing to remember, it has to evolve. And if there's no effort and then there's no will to evolve it, it will die off.
Indeed. In the interest of time, I see a lot of questions here from folks like Chuck. In fact, Chuck has a lot of these questions, as well as Mike Tsai about portability. So Chuck, if you have any, what's your most burning question here?
Okay, so I will down select in the interest of time. I think the two. I guess I'll go towards the one that I find particularly interesting right now. I'm sorry. Hold on, just a minute. I have children I have to mitigate. Here, can you circle back with me in just a minute?
Absolutely. Yeah, of course.
Thank
no
you,
problem.
Sorry.
Let's see. From CUDA to HIP. Mike Tsai. You had a question here about from CUDA to HIP, we have some challenge. We have to implement cooperative group for warp. Anything you want to share about that?
I think that is just an answer. So he was detailing. So it was actually Mike Tsai who did that effort in 3 weeks.
Not so much of a question, is it?
No, it was explaining the challenges that we faced. Some functionality was not supported.
All right, very good then. Let's circle to Roscoe again about his stability of a test suite.
Wait, the stability of the test suite?
How do you maintain the stability of a test suite you only run once a week?
Oh yeah, so we had this. So I worked with the Castle project for a long time, and it's a large nuclear reactor modeling physics code and some very expensive problems. And we tried a weekly test suite. So I think it was, I forgot who mentioned the test they only run once a week, but we found that it was practically impossible to keep that test suite clean because you really only got feedback once a week, and by the time you fix something, then something else broke. So so weekly was actually a bad name for that test suite we found, so we changed it to heavy. And then we just purchased a very beefy machine that we could run everything, and then we just ran that really heavy test suite once a day, and then it was something that we could maintain. But yeah, it's really critical to have different layers of testing where you have a very fast test suite for your pre-push tests, and then you've got one that runs after push where you have a beefier machine to run it on, and then one you run nightly on different platforms, and then a lot of projects really do need that heavy test suite to do, you know, order of accuracy testing, verification testing, closer to acceptance testing for, you know, real problems that you would run, like scalability testing. So it's really critical to have those layers. But yeah.
Yeah,
I think I was the one. I think I was the one who first mentioned the weekly test suite, and we actually struggle with the same thing. So I don't have a great answer for that.
Just buy a big machine and run them every day.
If you have the resources, what if you don't?
Then
So
you have to
the
make
whole
your test run
testing
faster. Yeah.
Exactly. That's actually what motivated what got reported in that paper, is that the test suite ran on people's workstations at night, and then it got to a point where people would come in the morning and the test suite would still be running. So we had to do something about it.
Mm-hmm.
Yeah, Russ, the bit that I'll throw on top of your suggestion of layering the test suite is if you do build up those layers from like unit at the bottom up through integration or user acceptance or whatever the top layer is, the encouragement I would have for you is anytime a test fails in one of the upper layers, try to replicate the problem with the test at the layer below, because each lower layer should run faster, and anytime you find something up here, you got to make sure in the future you find it down here. Does that make sense?
Yes, and that was a policy in Castle too. I mean, it should be an extremely rare thing. So the probability of it, you have a failure. So just make some random change in your code. The probability that it'll be caught in a lower layer, or I guess a higher layer versus a lower layer should be less and less, right? So there should be like a near 100% chance it'll be caught in that base layer, and then and then next to that next layer, so that by the time you get to that top layer, that heavy test suite, there's extremely rare probability. But unfortunately, most codes are not. I mean, because sometimes that heavy layer then ends up looking at real performance. It's not really correctness testing. You shouldn't be at correctness testing at that heavy level. I don't think we should be good enough at writing automated tests that we catch correctness issues at a lower level, but you can't really catch those performance issues and skill issues until you get to a very high level. But the probability of having a failure should get less and less as you go up. So.
Actually, I just want to throw in a comment over there. I'm curious for folks in this discussion, to what extent are the approaches, testing approaches you're involved in, unique to scientific software? And I think it seems like scientific software can offer some opportunities to make testing more efficient, like the application is capturing a science phenomenon. So you have invariants where people do commercial software. They don't really have known scientific invariants they can check for and things like that. That relates more to correctness, but at the same time, we care about scalability and performance. I'm just wondering are there any insights from scientific software that allows us to do a better job with testing than what people would do with non-scientific software?
So
well, I can, sorry, please go ahead, Anshu.
No, go ahead.
I just wanted to mention that we experimented a little in the direction of continuous benchmarking. So as we are focusing on high performance, we went in the direction of setting not only continuous integration, but also continuous benchmarking, where the tests basically are benchmark tests. And you then archive all your benchmark results. And the benefit is that you see on the one hand, if you did a change that degrades performance, but you also see if a compiler changed and suddenly the performance drops or increases, whatever. So you notice that. I think this is something that is relevant for scientific software. I could imagine that this is also relevant for other fields, but of course it's coming from the HPC line, let's say. Yeah. Please, Anshu.
So this has been my favorite soapbox for a long time, in the sense of how what is understood in the software engineering world doesn't really apply as is to the scientific software, because in some cases, in many cases, the needs are very different and the challenges are very different. Testing in particular is a really hard thing to do, more so even for the application codes than even for other kinds of scientific software, such as math libraries, etc. Because when you're doing exploration in science, you're almost never running the code in the same way twice. And those kinds of nuances, to capture those nuances in a test suite is a really challenging thing to do. And so I would say as much creativity and thought goes into devising tests as goes in devising algorithms themselves.
I guess at least my definition of scientific software is software that uses a lot of floating point arithmetics. That's what distinguishes it from the rest, right? So the problem that we face are the problems of round-off errors and how they affect the output result. What I find helpful, at least for regression tests, to run all the iterative solvers with with lowest tolerance available. This way, even if you have some round-off errors, they will be suppressed by the iterative process.
It's not as simple as floating point, because the scientific software is used for the purpose of exploration, which means that you are forever running it in regimes where you haven't run it before. Otherwise, there's no point in running it.
I agree. I'm just offering, a bit of my experience, how to deal with those things.
Yeah.
Very good.
Before we leave this,
yeah, go ahead.
Add something quick to that. One way you can take that a step further is convergence testing. If you have an algorithm that is supposed to be, say, second order, run the series of tests regularly to make sure that it is converging to second order. That's one way of getting a little more general form of what we were talking about a moment ago.
So I think testing in a scientific, it should be true in every software, but it's particularly true in scientific software, is that verification is not just testing. Verification is beyond testing. So you are testing not just for correctness or the expected behavior, you're also testing for all sorts of other things like stability, convergence, as Vivek pointed out, the conservation of quantities, figuring out your error bars, et cetera, et cetera. So I think it's a richer research field in its own right than a lot of the kind of testing that happens in non-exploratory software.
Yep. Jason, you had a point to make before we move on?
Yeah, just the last thought that was triggered by conversation a few minutes ago at this point. I think this may tee up some of our conversation for tomorrow, but as we talk about, devoting time and energy to test suites, to developing, to architecting them well, to making sure that whatever code gets committed gets adequately tested, I think all of this needs to somehow come up in whatever performance review process exists in your organization. I mean, we definitely have a history of awarding scientific output for sure, and for good reason. But we also need to take into consideration the testing that enables that scientific output. And I don't think it's going too far to say that, if that when it comes to leading projects, to leading codes or organizations well, we need to have the courage to say that, come performance review time, whatever that looks like for you guys, like your scientific output is stellar, absolutely amazing, and that's what we desperately need. But your testing of all of the code that you write for the sake of that scientific output needs some serious improvement. And unless we see that serious improvement, that could jeopardize your position on the team or with the organization or whatever. I haven't seen that kind of daring leadership in that direction yet. And I wonder what it means for us in terms of future maintainability of everything we're working on.
Oh, that is a great bunch of stuff to tee up for tomorrow, especially with cultural. That's great. I love it. Also, there's a question here from Jan Patrick about what kind of incentives, what metrics are suitable to convince management for adopting investing time into things like CI. I think in the interest of time, Jan Patrick, you should definitely get that question in tomorrow, because I think that's also a cultural thing. It's a blending of technical and cultural. We do just have about 3 minutes left. I was going to jump back to Chuck and see if he was ready with it to pick just one question that we can address in about 3 minutes.
Yeah. So there was a lot of discussion on portability and the tooling to put in place to kind of port to different GPU architectures, and how that's really enabled productivity, and kind of abstracting your algorithm to not depend on things that are specific to the architecture. I'm curious how the panelists feel with respect to how that translates to some of the other newer non-accelerator based architectures. So you're looking at like Fujitsu's ARM platform, things like that, where you're not looking at GPUs anymore, and it's not just porting to different GPUs, and your algorithm structure might not really map the same.
All right, 3 minutes, panel. 2 minutes. What do you got? Anybody jump in?
Well, even if you look at just ARMs versus GPUs, or even comparing those to where CPUs are going now, they all have this commonality where you have lots of small processors of some form, lots of need for memory locality, not lots of need for putting doing computation on whatever you draw from memory a lot before you put it back, instead of constantly going back and forth to memory. So that buys you, even among these architectures that have some superficial differences, they have that deep thing in common. So designing for that is going to help you across the board.
Go ahead, Anshu.
Invest in design. Invest in design. Software design. Instead of designing for the next available platform, design with parameterization of your working set, of your data locality, and then it's much easier to have configurability at finer and finer granularity within the code. And that's how you can actually solve this problem. That's the approach we are taking.
And on a completely different note, I'll just reinforce the two themes. I think there's no escaping asynchronous tasks and there's no escaping Python. So embrace them. I think if you do more with Python, you'll find you can also, it helps with your workforce pool, talent pool development. Undergraduate interns and graduate interns can contribute more productively over there and come up to speed. So I think they're both here to stay.
Any final thoughts from anyone else?
So I would echo Anshu, design your software. That's what we did. And therefore, I think for us, the move wouldn't be really hard. So it's just another backend for us. The algorithms are separate, so we don't have to rewrite a whole lot of code.
Yeah, very good. Well, panel, it's 12:31. Thank you very much for all your thoughts. Thank you for the questions from the audience. If we didn't get to your question, I'm very sorry. There's been a lot of activity here, but fortunately we have day 2 Slack chat. So get right in there and we can continue the conversation. Let me share the screen again. Hold on a second, let me move you, excuse me. Share screen.
I have a suggestion.
Please.
So everybody who posted their questions and didn't get an answer, would you please post them in day 1 chat?
Day 2 chat.
Day 2 chat.
Oh, day 2? Okay.
Yep.
Yeah.
It's day 2. All right. So the next Zoom session starts promptly at 12:30, and at 12:35, like yesterday, we'll move to breakout rooms. The discussions are scheduled from 12:30 to 2. All times are central again. And then posters and tea time themed discussions will be at 3 p.m. Also, before we go, I'm going to make a shameless plug. SciAm CSE 21 is now accepting submissions for mini symposia. The deadline is August 10th. And one of the themes this year includes numeric software sustainability. And I think it's probably not a big leap from there to productivity. So, I mean, it would be great to have these kinds of conversations continue in a community like that as well. So I'd love to see some of those submissions. if there are any questions, or Mike, if you have anything else before we adjourn.
No, thank you very much. Great session. Lots of good conversation. Thank you, everybody.
All right. Well, thank you all very much, and
Thank
we'll
you.
see you later.